Hello students and welcome to 5.02 phase changes teaching video. Some of our common core objectives is to cite specific textual evidence to support analysis of science and technical text. Then we're going to differentiate among the four states of matter and also describe phase transitions in terms of kinetic molecular theory. And then in the lesson itself, you will also find these two objectives: identify phase changes as physical changes, and describe phase changes in terms of kinetic energy and intermolecular forces of attraction. So in lesson 502, you're first introduced to the different types of phase changes that can occur. The first two that we got up here are melting and freezing. In melting, we're going from a solid to a liquid. Freezing is just the opposite, where we're going from a liquid into a solid. All right, so let's first look at the melting one here. All right, we're starting with a solid, and we add heat to the solid. As we are adding heat, we are of course going to increase the kinetic energy of the particles. As a result, the particles are going to be vibrating more and more violently is a word that we use sometimes there, but they are going to be vibrating more. And at a certain point, we're going to add enough heat that they're going to be vibrating so much that they're going to be able to overcome the attractive forces between them. Now, they're not going to be able to overcome them enough to fully separate and get away from each other, but they are going to be able to separate enough, or break, I should say, the intermolecular forces enough that instead of being in fixed positions, they can now at least move around each other. If you watch the lesson 501 video, I used the illustration of if you put a bunch of people into an elevator, they have fixed positions, right? Everybody stands in their spot. While they're standing in their spot, they can wiggle around. Well, that's kind of like a solid. Everybody has, or every particle has a fixed position, but they're able to vibrate. Well, in the liquid, they're still the same people in that elevator, but now instead of being in fixed positions, they are able to move around in the elevator. So they are flowing. They're able to slide past each other and move to different positions in the elevator. That would be a liquid. So when you heat the solid, you add enough kinetic energy that the forces that hold them in those fixed positions are broken and they are now able to move around. But they still have intermolecular forces between them that are keeping them in the elevator, if you will, following that analogy. Now, at a certain point, of course, is when that occurs. We call that the melting point, temperature at which that given substance melts. Okay? Now, if we have those particles flowing, moving, and we start removing energy, okay, we do just the opposite. Instead of adding heat energy, we remove heat energy. Well, the particles are going to start to slow down. As they begin to slow down, they are going to reconnect, if you will, with those intermolecular forces, and they're going to go back into fixed positions. So again, using the elevator analogy, those people that are moving start moving slower and slower and slower until they get to a point where they all stop. They are now in their fixed positions again, but they are still able to wiggle or vibrate, if you will, in that fixed position. That occurs at what's called the freezing point. Now, the neat thing about this is for any given substance, the freezing point and the melting point are the same. Okay? So if we have a solid changing into a liquid, it's going to happen at the same temperature that the liquid version would change into the solid. Okay, so again, freezing and melting happen at the same temperature. So if we have a solid and we're changing it into a liquid, and let's just use water for an example, that happens at 0 degrees Celsius. Well, if we take that liquid water and we go the other direction and change it back into the solid, so we're freezing it, well, it also happens at 0 degrees Celsius. The difference is the heat exchange. In the first one, solid to liquid, we are adding heat, whereas in the second situation, going liquid to solid, we are removing heat. Okay, but overall, it's happening at the same temperature. So a very important note there. Now remember when you are freezing or melting, or the other phase changes we're going to look at, in the, using the water example here, we start with H2O in the solid form, we end with H2O in the liquid form. It's still H2O, chemical properties have not changed, therefore that is a physical change that is occurring. Alright, now the next type of phase change we're going to look at is evaporation. Evaporation is now when we go from a liquid to a gas. So now we have the molecules that are flowing. They have more energy than the solid, but they still have those intermolecular forces holding them close together. So we continue to add heat to it. Well, as we add heat, those liquid particles continue to move faster. They continue to flow past one another more quickly. And at a certain point, we're going to have enough kinetic energy that some of those liquid particles are actually able to escape and become a gas. That is what we call boiling, when the temperature is high enough that the evaporation is occurring within the sample of the liquid instead of just at the surface. Alright, now just a little side note here for water. It actually is about 7 times as much energy to vaporize as it is to melt. And it may not necessarily always be 7 times with other substances, but generally speaking, it is going to take more energy to evaporate or boil something than it is to melt that substance. It's just naturally going to take more energy to do that because there's more intermolecular forces that we have to overcome to make that happen. Now there is a certain point at which that occurs, and that is what we call the boiling point, temperature at which a substance boils. And of course we all know for water that's 100 degrees Celsius. So again, evaporation, just to clarify here, happens at the surface of the liquid. So say you have, a glass of water, and if you leave it sit on the counter over many days, you know that there is less water in the cup because it is evaporating. Some of those liquid particles have gained enough energy that they escape from the surface in the form of water vapor or gas. Boiling, we can take that same water, put it on the stove, and we add heat energy to it, and now we are putting heat energy throughout all of the water molecules, not just the ones on the surface. So now we have liquid changing into gas form within the substance, which is allowing them to then, of course, rise to the top and escape. Okay, so that's evaporating. The opposite of evaporating is condensation. Okay, so going from gas back to a liquid. So now if we have these gas particles that are spread out, have no interactions with one another, so they're doing their own thing, free to move about, we start removing energy from them. So they start slowing down. Well, as they start slowing down, they start getting a little closer together, and they begin to have attraction for each other. Well, as they reform those intermolecular forces, that will draw them back together, forming a liquid. Okay, that occurs also at a particular temperature, and that's called the condensation point. It's not a phrase that you typically hear, but it is, the proper term for that. It's temperature at which, the gas goes into the liquid form. Now again, just like with melting and freezing, boiling point and condensation point are at the same temperature for any given substance. So again, if we take the liquid and we convert it into gas, and again I'll use water for our example, we know that happens at 100 degrees Celsius. If we turn that around, we take the gas and we convert it back into the liquid, it's going to condense at 100 degrees Celsius. So again, different phase change, but it's happening at the same temperature. Just like with melting and freezing, the difference is the heat exchange. So when we're going from liquid to gas, we are adding heat. And then when we are going from the gas back to the liquid, we are removing the heat. All right, now we like to represent all of this in heating and cooling curves. Here we have a heating curve, and what you get on the heating curve is you got the energy that's added going along the x-axis, and you have the temperature of the substance on the y-axis. Now, when it's in its solid state and you begin to add energy, the temperature will continue to rise until it gets to the melting point. Once we hit the melting point, all the energy that's being added is being used to change the solid into a liquid. Once we get to this point over here, all of the solid has now been converted into liquid, so as we continue to add the heat energy, it's just going to raise the temperature of the liquid until the temperature reaches the boiling point. Once we reach the boiling point, now all the energy that's added is going to be used to turn the liquid into a gas. Once it's all into a gas, as we continue to add heat energy, it's just going to raise the temperature of the gas. Now in this particular example here, you notice our heating curve, the melting point is at 0 degrees Celsius. The boiling point is at 100 degrees Celsius. So this particular heating curve is for water. And we know that because water melts at 0 degrees Celsius and boils at 100 degrees Celsius. Okay, so as we are going left to right here, this part of the graph represents melting. And this part of the graph represents boiling. And again, overall, we are going from left to right following the diagram here. Now, if we take this diagram and simply flip it or reverse it, we now have what's called a cooling curve. So let's look at a cooling curve. Okay, so now, again, all we did was just flip it or reverse it, however you want to think of it. We now have the gas here at the beginning. As we remove heat energy, it begins to cool until it reaches the condensation point, which is also the boiling point. Once we hit that point, it no longer can exist as a gas, so all the heat that's being removed is causing the gas to be changed into a liquid. Once it's all converted into a liquid, as we continue to remove energy, it just simply cools the temperature of the liquid until it reaches the freezing point, again, which is also the melting point. Once we hit that point, the liquid can no longer exist, so the energy removed causes the liquid to structure itself, the intermolecular forces re-engage, so to speak, and it changes it into a solid. Once we get everything into the solid and we continue to remove energy, it simply cools the temperature or lowers the temperature of the solid. So for this one, as we are going gas to liquid, that flat plateau near the top there, that is the condensation going on. And then the smaller plateau near the bottom here, this is freezing. All right, and again, we are following this graph from left to right, just like we did the last one. All right, now earlier on we had mentioned that the amount of energy needed to boil something is greater than the amount of energy that is needed to freeze something. Well, if you look here at our diagram, that's represented by the plateaus, right? The longer the plateau, the more energy is needed, whether it's added or removed, for that process to occur. So you can see that it takes more energy removal for condensation than it does for freezing. If we go back to the last slide, we see that again when we're heating things. We have a small plateau for melting. We have a larger plateau for the boiling. So it takes more energy to boil the substance than it does to melt the substance. So that's an important relationship there to remember. Again, the other important relationship is to remember that these do occur at the same temperatures. So boiling and condensation are happening at the same temperature for the same substance, and freezing and melting happen at the same temperature for the same substance. Now in this example, again we have 100 for the condensation point and 0 for the freezing point, so again we are dealing with water. Even though it's a cooling curve, it's still just water. Okay, but all substances will have similar looking curves. It's just a matter of how much energy is added or removed, and then what their melting point and boiling points are. Okay, so what's next? All right, well, now that you've watched the video, you can make sure you complete all the parts of 5.02. If you still need some help, please attend the open tutoring sessions. There is a review sheet in the Student Resource Center that you can use. In the Activities tab, there is a review section that you can also use to help. And once you have learned all the material, feel comfortable with it, in the Assessment tab, or Assessment section, or the Gradebook section, you can click on the 5.02 quiz, and then you can complete that quiz and move on to assignment 5.03. I hope this was helpful, and we look forward to seeing you again soon.